Having studied continuous functions, we're now going to take a look at properties of continuous functions. So we're going to start with a theorem that tells us that if we have a few basic continuous functions, then we can build new functions through addition, subtraction, multiplication, and division of those functions, which we can then conclude are continuous without having to actually prove they are continuous. So this is an important result, and let's take a look at it. So we're going to let b be any real number, and we're going to let f and g be two continuous functions at a point c. Then the following functions are also continuous at c. b times f, where b is any constant. F plus or minus g will be continuous. F times g will be continuous. And the quotient f divided by g will be continuous, provided that g of c doesn't equal 0. We don't want to divide by 0. Alright, so let's take a look at how we use this, and then eventually we'll prove one of these. So let's start with this example. So we want to show that f of x equals x and g of x equals sine x are continuous over all the real numbers, and then we want to argue that this function, which is built from x and sine x, is also continuous over all the real numbers. Well, recall that to show a function is continuous, we have to show that this is our statement of continuity. We have to show limit as x approaches c of f of x equals f of c exists. Well, certainly this is true for x and sine x, because certainly the limit as x approaches c of x equals c, and that's f of c, and the limit as x approaches c of sine x equals sine c for all real numbers c. Now this one right here, we didn't actually prove this, but we looked at the graph of sine x and saw it was nice and smooth, so this is going to be true. Later on we'll prove that sine x is differentiable, which will actually prove continuity, but we need to look at that result later. So now, notice that if x and sine x are continuous, then we can argue that the following are also continuous by properties 1, 2, and 3. So let's say by 1, 2, and 3, 5x cubed, x squared, negative 7x, and sine squared x are all going to be continuous as well over all the real numbers. For example, we can conclude 5x cubed is continuous because all we have to do is multiply x by itself once and then twice, or just 3 times, using property number 3, and so we get that x cubed is continuous, and then just multiply by the constant 5, that's property number 1, so certainly this is continuous. And then by property number 2 again, we can conclude that when we add all of these up, that it's going to be continuous. So then we can argue that when we add all of them up, this is continuous over all the real numbers as well. So that's how we use this theorem to build very complicated looking functions which we know are continuous from just a few basic functions that we know are continuous. Now let's take a look at the proof of number 2 down here. So if we're given that f and g are continuous at x equals c, we want to show f plus and minus g is continuous. So if these are continuous, that implies that the limit as x approaches c of f of x equals f of c, and that must exist, and the same thing for g. So if we then look at the limit of f of x plus or minus g of x, we get this. And so the limit as x approaches c of f of x plus or minus g of x, we can distribute the word limit by our previous results for limits, like this. This part right here is f of c. This part right here is g of c, as we have written right here, which exists. And therefore, f of x plus or minus g of x is going to be continuous at x equaling c. So that's the proof of number 2, and the other ones are proved in a similar manner. So let's take a look at another example. So we're going to look at some examples down here. Now before we do that, we have a quick theorem here to mention. This theorem is a result of the previous result, and it says that the following functions are continuous at every number x in their domain. Polynomials, they are actually continuous everywhere for all real numbers x. Rational functions, they're all continuous everywhere except where q is equal to 0. Radical functions are all continuous, as are trigonometric functions. Alright, now just to mention something here about the polynomials, the reason that this theorem follows from our previous theorem is, for example, if we look at number 1 here, if we wanted to prove that all polynomials are continuous, well, remember we just showed that x is a continuous function. So of course, x squared, x cubed, all the way out to x to the n, these are all continuous functions. And so if I multiply them by the constants an minus 1, and so on, all of these are going to be continuous. All of these are going to be continuous. And so if I add them together, I'm going to get a continuous function by property number 2 from above, and that's the one we just proved. Alright, so that's why you have all of these results. Now let's take a look at this example. So we want to determine the domain over which the following functions are continuous. So first of all, let's take a look at sine x over x squared plus 1. Well, notice that this is the product of two functions. It's the product of the sine x times 1 over x squared plus 1. Now the sine x, this is continuous everywhere over all the real numbers. So we'll write that down here. Or negative infinity to infinity you could write. Now 1 over x squared plus 1, that's also going to be continuous over all the real numbers because x squared plus 1 is never equal to 0. The only place this function would have any trouble being continuous is where the denominator is 0, but you know, x squared plus 1 is never 0. Remember, if you tried to solve, you would get x squared equals negative 1, but there is no solution to that. No solution. Okay, so 1 over x squared plus 1 is also continuous over all the real numbers, and so therefore this function is continuous over all the real numbers as well. Now let's take a look at this one, square root x squared minus 4. Well, let's notice that the square root of x, that's only continuous for x greater than or equal to 0. So this is continuous for x greater than or equal to 0. Now, if I look at 1 over x squared minus 4, that is going to be continuous for all the real numbers except Well, when the denominator is equal to 0. And when is the denominator equal to 0? Well, if we solve x squared minus 4 equaling 0, that means that x equals plus and minus 2, right? Okay, so this is continuous for all real numbers except plus and minus 2. Okay, so what we have then is that this function here, the square root x over x squared minus 4, is going to be continuous over the interval from 0 up to 2, but not including 2, union 2 to infinity, like this. Notice we had to exclude the number 2 because that's where the denominator is equal to 0. And we're only considering positive real numbers, or real numbers greater than or equal to 0, because that's where the square root of x is defined. Alright, and that's our answer. Now let's take a look at one more theorem. We're not going to look at the proof of number 1. We already talked through that one. So this is talking about the continuity of the composition of functions. So we assume that g of x is continuous at x equaling c, and f of x is continuous at g of c. Then the composition function f of g of x is continuous at x equaling c. Now we're not going to prove this result. We're just going to talk about what it's telling us and look at some examples. So let's take a look at this problem. Let's write this as the composition of two functions and find where it is continuous. So let's notice for this function, if we let f of x equal the square root of x and g of x equal x squared minus 1, then the composition is going to be the square root of x squared minus 1. Alright, so we've written this function as the composition of two separate functions. Now, the square root function, square root of x, that is continuous for x greater than or equal to 0. And x squared minus 1 is continuous everywhere. That's a polynomial which is continuous everywhere. So what we have to do is we have to find where is this function going to be positive, greater than or equal to 0. Alright, so what we have to do then is we just have to set it equal to 0 first. Now notice that this is the same as writing, we can factor the x squared minus 1 as, and so that's equal to 0. That implies that x will be plus or minus 1. Alright, now to determine where this is positive and negative, we can just use a little sign pattern and pick test values in between, like -2, 0, and 2. If we plug these numbers into this function or this function, well, let's see, if we plug -2 in here, we're going to get back a positive number, right? So the function is positive from negative infinity to -1. If we put 0 in here, we're going to get a negative number back. So the function is negative from -1 to 1. If we put 2 in here, we're going to get back a positive number. Alright, 2 squared minus 1. Alright, so therefore, x squared minus 1 is greater than or equal to 0 for x for this interval. We'll write it like this. 1 to infinity. And so what we have then is we have that this function, the composition function, will then be continuous on this interval. So therefore will be continuous So you see up here, if you compare what we did with the theorem up here, the square root of x was playing the role of f. X squared plus 1 was playing the role of g. Now we know that for this particular example, g is continuous everywhere, but f of x is only continuous for positive x values. So we had to find where the g, in our case, was greater than or equal to 0. And so that's exactly what we did, you see. We set the g right here, greater than or equal to 0. And then we found what x values made it greater than or equal to 0. And that's going to be where our composition function is going to be continuous. All right. And so right here is what the graph of that function looks like. So right here is -1, and right here is +1, and you can see the graph does look like it's continuous from -infinity to -1, and then from 1 to +infinity. So it's continuous over this region and this region. All right. One final example. So let's take this function and write it as the composition of two functions and explain why it is continuous everywhere for all x. Well, we notice that if we let f of x equal the sine x and g of x right, then f of g of x is this function. All right. Now the sine function is continuous everywhere. That's continuous for all x. So there is no restriction in what we have to, in what g can be, right? You see right here's my g. So there's going to be no restriction in what this value, this function in here can equal. And also, x squared plus 1, well, of course, that's also continuous for all x as well, for all real numbers x. And since there is no restriction on what we can put in for the sine function with respect to its continuity, therefore, the sine of x squared plus 1 is continuous over -infinity to infinity. Okay. And that completes our discussion about properties of continuity.